Alrighty, hey everyone, welcome to the Specialist 3-4 lecture. We'll get started. So, hey everyone, my name's Michelle. I graduated in 2018 and my VCE subjects mainly consisted of maths and science subjects, and then I also did mainstream English. And I think even though I'm not doing as much maths or in university anymore, there definitely is a good balance of the problem solving skills, and that kind of applies to regardless of what course you really do in the future. So definitely a lot of the things transfer across. And I'm currently studying med at Monash, and I'm actually in my final year now, so not much more longer to go. And I definitely think, even though VC was, a bit of a while ago for me, it definitely is something that helps you learn and helps you build the problem solving skills and also prioritization skills as well. Great, so just a little bit about ASHA notes. We've been around since 2007, and our goal and our mission is just to make sure students like you can get the support and resources they need to succeed. And we do that by trying to offer as much free resources as possible and as much different support things as we can. And we've done these lectures since about 2015, and we've moved towards kind of a hybrid model, with some of our lectures being online and some of our lectures being in person. So some of the stuff we offer stuff like free notes, we offer things like lectures like the ones happening now. And so regardless of what type of learner you are, regardless of if you prefer reading things and kind of getting your notes down, or if you're the type of person who likes the videos or kind of interactive learning, we have all of those types of things available. And we also have discussion forums where you can ask experienced tutors their opinions on questions or concerns that you might have. And if you feel like you need a little bit more support, we have a couple of resources like our Tute Smart program, our AG Unlimited study guides, and if you're kind of a more hard copy type of person, we've also got the study guides in print as well. Alright, but we'll jump into the lecture for now. So essentially we're going to have two blocks of learning today. So we'll have the first bit, which is a bit on calculus, so the differential equations, kinematics, and then vector calculus. And then the second block will be about logic and proof. There won't be a break between the blocks, but it's just kind of like two distinct topics. So just pause the video, have a break at any time, but just most importantly, please do ask questions in the chat. Any questions you have, questions are probably the best way to learn. Cool, so let's jump straight in then. So we'll talk a little bit about differential equations and how they work. So the idea of differential equations is that there's not going to be anything particularly new in this topic. The things that are going to be involved in this topic, the skills that you need for this topic will be already kind of present in your repertoire. So things like integration and differentiation are the things that you're going to use here. And in terms of the rules for them, you will have already learnt them in those calculus topics before. But the whole point is being able to apply those topics and apply that knowledge to doing a question which is more in an application sense. And that's what differential equations are. Cool. So essentially, when we talk about differential equations, it's kind of like talking about a polynomial, because what we're actually saying is we say differential equations of first degree, second degree, etc. And all that actually means is how many times we've derived that equation. So when it goes from y to dy dx to d squared y over dx squared, we go from, first degree to second degree derivatives, and that's kind of similar to first degree and second degree polynomials. So some, like the name suggests, the equations themselves, they'll have derivatives, and that's the whole idea of a derivative equation or a differential equation. So what we want to do is we want to do differentiation and integration normally, but then we're going to use those types of skills to actually solve their equations. Just like we have this whole repertoire of things that we do for polynomials, it's also building this repertoire of things that we use to deal with the differential equations. There's kind of two types of questions that they ask here. So they might ask you to just solve one of these antiderivative equations, and that, is potential what they want you to do. Another type of question is they just ask you verify or show that. And often because these actual derivatives and things are actually quite complicated to do, and it's a bit difficult to antiderive something, or it's a bit difficult to derive something, often what they actually want you to do is just to prove that one of these things is a solution rather than coming it up with yourself, because it can be a bit tricky to do that. And if they want you to do that, it will normally be in the context of like an exam 1 question where you don't have a calculator around as well. Cool. Alright, so these differential equations are going to be classified by the order they're given in. So like we talked about before, if you have the first derivative, it's going to be a first order differential equation, and if you have the second derivative involved, which like this one, it's going to be a second order differential equation. So essentially pretty reasonable in terms of how they name it. So if you derive it once, it's first degree. If you derive it twice, it's second degree. If you derive it 3 times, it would be third degree. So you kind of get the drill from there. So that's kind of different. That's how differential equations are named and works. So in terms of actually doing it, so like I said, there's actually 2 different types of questions. There's verifying and then solving, right? So the verifying one normally kind of relates to more when you're talking about doing a differentiation on a complex equation that you're dealing with, whereas when we talk about solving, normally you're doing more anti-differentiation and kind of doing with those types of things more. In terms of the steps, you'll get a differential equation and you'll get a solution to it for verification, and your job is to essentially prove that solution works. So you have to show it all working out, because these questions will be show that questions. And essentially the key thing to do here is you want to pick one side, often the more complicated side, and just keep working on that side until you get your desired result, and kind of manipulate it so it fits with the other side, and then you can equate both sides. If you want to solve differential equations, you'll get a differential equation and then you'll get conditions for that differential equation. Because remember, when we integrate, we essentially get a family of functions. We don't get an individual function. So we need an anchoring point to tell us exactly what function it is. So if we're looking at something like this, right, and we anti-diff to get a parabola, it could be here, 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 could be here, it could be here, it could be here. So, it could be anywhere along that line. And so the whole point is we need at least one point in the line to tell us exactly where it's passing through. And these will mostly be first derivative ones, unless they are super duper straightforward and it just literally says d squared y over dx squared equals to something. In that case, still a second order differential equation, but not really, we don't really have to deal with the universe of the differential equations, more just integrating twice. Cool. Alright, so let's talk about this question here. So the number of mobile phones N owned by a certain community T is going to be modeled by this equation. So 6 minus 3t negative 0.4t, where t is bigger than 0. So they want us to verify by substitution that log en 6 minus 0.4t, or negative 0.4t, satisfies this differential equation. Okay, so we look at this side. This side is evidently more complicated, so that's what we're going to work on. So we can essentially say that we're going to get that we want to say that the left hand side will equal to 1 on n dn on dt plus 0.4 log en minus 2.4. Right, cool. So that's what we can do here, and so this is our kind of log en equation in terms of what the equation actually is. And then now what we need to find is, the extra thing that we need to find here is we need to find out what dn over dt is going to be equivalent to. So dn on dt is going to just be equivalent to us deriving this, or we can just derive both sides because we need to do a bit of implicit differentiation here. So if we do d of dt times log en, and that's equivalent to d on dt times 6 minus 3 e to the negative 0.4t. So on this side we'll just have dn dt times 1 on n, which is going to be equivalent to the 0 is going to disappear into nothingness, and we're going to get negative 3 times negative 0.4 times e to the negative 0.4t. which is just going to give us 1.2 e to the 0 into point negative 4t. Cool. Alright, so we've got that part. So essentially we've got the first part of the equation. Now, what we can say is therefore our left-hand side is just going to equal to this equation that we've just found here, which is 1.2 e to the negative 0.4t plus 0.4 times our log en, which is equivalent to 6 minus 0.3 e to the negative 0. Well, that kind of went off the page. Negative 0. Let's rewrite that part. Minus 3 e to the negative 0.4t. So all that's going to work out to be is 1.4 e to the negative 0.4t plus 2.4 minus 1.2 e to the negative 0.4t. So therefore that's all going to be equivalent to, you can see how those two cancel out, is just that it's going to be, then there's also a 2.4 at the end as well that we've got to add on. So plus 2.4 and plus 2.4, right? Or minus 2.4, sorry, not plus. Minus 2.4 and minus 2.4. So what we're going to get in the end is that we'll see that the minus 2.4 cancels out with the minus 2.4 and the 1.2 will cancel out with the 1.2, so that will just give us 0, which will give us right hand side as required. Cool, so we can kind of see how that all correlates together to give us the answer we need. Amazing. Right, so in order to do the separable differential first order equations, remember like to like. So essentially all you need to think about is, it's kind of a bit of dodgy maths to be really honest, but if you have something like dy dx equals to blah, essentially what you do is you separate the dx to this side and keep the dy onto this side, or you can flip the dy dx depending on whether you have y as the subject or whatever. But the key thing here is that you essentially separate them over. So you would theoretically think that, oh yeah, you would have blah dy equals to blah dx, but that's actually not mathematically correct. So just make sure when you're doing that step just to add the integral sign at the front, and now suddenly that is mathematically correct. So you can just do something like that. So what you want to do is you want to rearrange, so x and dx is on one side and y and dy is on one side, and dy and dx are actually going to be numerators. So in differentiation you have d over dx, which is you can see that the dx, or the factor that you're doing it by, is the denominator. In terms of integration, it's actually the numerator instead. Then what you're going to do is integrate both sides as per normal, because you have your function in terms of y and then you have your function in terms of x. And you can put the plus c on the x side. And then you can make y the subject to kind of rearrange your function and get your function down. Cool. Alright, let's clear that screen. So you can kind of see like this one. So if you have dy dx equals to fx gx, you can see that the fx goes onto, the dx goes onto this side and the gx comes to this side. So you'll get 1 on gx dy and fx dx. So then you can put the integral signs out the front of both of them, and that will give you your function that you want. I would say you don't need to put the plus c until you actually do the integration. So you would do the integration, you would get big fx plus c, so where big fx is your antiderivative. Okay, cool. Alright, so for example, something like this. So we have solved the following differential equation where dy dx equals to y over 1 plus x squared, where y0 equals to 1. So this is to solve that question. So we can see that we have the actual derivative, and then we also have an anchoring point to tell us exactly which in the family of functions is going to be. So then what we want to do here is get the dy and the dx on the same side. So we're going to move the y to one side. So we're going to get 1 on y dy is going to be equivalent to, and we're going to move the dx to the other side, 1 on 1 plus x squared dx. And then to make sure it's mathematically correct, we're going to just put the integrals in front of it. So 1 on y dy is just going to be log ey. And this one, if we kind of look at what type of thing this might be, this is going to remind us of our tan inverse function. So it's essentially just going to be tan inverse of x. And then we can put a plus c on the side. So therefore what we're going to get here is that modulus of y would equal e to the power of tan inverse x plus c, right? And then because e of x, or e of a, is always going to be bigger than 0, therefore you'll just get that y will equal to e tan inverse x plus c, because it will always be positive and y will never be in a negative kind of position. Cool. Alright, so then what you can do is you can sub in the 0 point, so you can sub in 0, 1, so we'll have that this is going to be 1 equals e to the power of tan inverse 0 plus c. So therefore we'll get that this is going to be e to the tan inverse 0, and if we think of what the inverse angle to 0 is, so when tan is equivalent to 0, that's just going to be when you get 0, right? Because you'll have sine equaling to 0 and cos equaling to 1 or whatever. And so that's when you're going to get 0 there. So essentially we'll just have 1 plus e to the power of 0 plus c. 1 equals e to the power of 0 plus c. So 1 will equal to e to the power of c, and c will therefore equal to log e1. Or alternatively, you can say what power would e need to be raised to reach 1, and we can conclude that c actually equals to 0 here. So therefore, in terms of the actual equation, so equation would be simply just y equals to e to the negative tan to the negative inverse x. Cool. So we can see we separated it out first, did the integration, right, sorted out the integration, and then rearranged to make everything nice and pretty. Okay, cool. So there's heaps and heaps of applications of differential equations. The main three things that you'll kind of see across your thing is growth and decay, concentration and mixing, and then the other one we'll be talking about like logistic equations and all that kind of stuff. So growth and decay, these often work on exponential models. Or when you're talking about cooling, which often is also an exponential model, and essentially what it is like if you were to set out a glass of tea on the side of your room, how long will it take for that glass of tea to cool to, I don't know, 30 degrees or something? So it's kind of that type of question. Concentration and mixing questions often people find a bit tricky, which is fair enough. The key thing to think about is what goes in and what comes out, and therefore what is overall change. So if we're looking at something which is growth or decay, which is proportional to the population, right? So what we'll get is that, you know, if y equals to the population, we'll get that dy dt will equal to ky. So therefore you'll get that y by itself will just be equal to a times e to the power of kt, right? And if k was bigger than 0, this means that this graph would grow. And if this t was smaller than 0, if the k was smaller than 0, that would mean that the graph would just shrink, right? In terms of the, like, whether it's going up or whether it's increasing, whether it's decreasing, right? So if the k is smaller than 0, that means that it's like 1 over something. So as the thing, because it's 1 over e to the power of kt, or negative kt essentially, because that's going to be positive because this one was negative in the first place. And if you think about increasing the value at the bottom, you're going to be dividing by an increasing larger number. So therefore what you're going to actually get, instead of an increased value of y, you're going to get a decreased one, because you're dividing the number by a bigger and bigger number. Cool. And a is essentially just going to be our initial population or initial whatever, but often it's just given a random variable. As long as you know, like, it doesn't have to be a, but as long as you know that there is existing a variable, that's totally fine. Cool. So this alien population is increasing, and the rate of alien increase is proportional to the number of aliens present at any time t. So there is usually about 500 aliens, and they're growing at a rate of 100 per day. So what is going to be k? So what we can do here is essentially just set up that equation that we just did for the previous question, and essentially say that if you know that at t0 population p equal to 500, and it's growing at a rate of 100 per day. So what that means is you know that dp dt equals to 100, right? So you can kind of apply that into our function here, because we know that it's going to be proportional to the population, and it's 100. So the rate of increase is proportional to the number of aliens, so that will mean that dp dt will equal to k of p. So therefore k of p will equal to our 100, right? And our p was equivalent initially to 500. So, when it was equivalent to 0, it was equivalent to, when t was equivalent to 0, we can see that this was equivalent to 500. So essentially you're going to get that this is going to be 500 times k, which equals to 100. And because it's initially growing, that the initial rate for this growth of aliens, so growth of aliens at rate of k equals to 1/5 aliens per day. Cool, awesome. Alright, so solve the differential equation to express p as a function. So what can we say? We can essentially use that equation from the previous one and put that in, so that you know that your p value is going to essentially be equivalent. So there's kind of like two ways to do it, right? You can either write it out exactly as you've done here, so you don't have to worry about it too much when you're going into detail about it. So what you can do is essentially you can say that your y, so you can say that your dy dt, dy or dp dt, just erase that. So your dp dt was going to be equivalent to 500 times k, which was going to be, or your p times your 500. So initially it was 500, and then so it would have been 1/5 of p. So therefore, if you're going to try and find out what that is going to be, you'll get that dt over dp is going to be equivalent to 5/p. So therefore your t value, so you want to find t at any time t, and you know that at t equals to 0, your population is going to equal to your 500. So what you're going to get here is that you can say that from t to 0, let's say 1 dt is going to be equivalent to p to 500 5/p dp. So you can kind of see how we move that to this side and move that to this side. So we'll have t minus 0 will be equivalent to 5 log EP p 500. So t will be equivalent to 5 log EP, and p is bigger than 0, so we can leave it as that, minus 5 log E 500, which will essentially just give us that this is going to be all divided by 5. So t over 5 will equal to log E p over 500. So e to the negative t over 5 will equal to p over 500. So therefore the final thing you'll get for p is p will be equal to 500 e to the negative 1/5 t. And if we check that with the equation that we just wrote out here, we can see that that's going to be the exact same, right? So because it's going to be growing at that rate of 100 per day, we can kind of see how that's going to be equivalent to the one that we just talked about before. And you can kind of see how when we subbed in that 500 gave us the same thing. So that's exactly what's going to be happening here in terms of our equation when we're kind of dividing across and moving that across. So I think this should actually, this should just be positive 1/5. So you'll get that this is going to be increasing by essentially 1/5 every time. So as this increases, you're going to be increasing to infinity and beyond. So you can say that this would be that number of aliens. Cool. Alright, so another application which is quite similar to it is often they like to talk about like cooling or kind of warming up, and it's really based on, I've seen lots of questions where like they've had something in one environment, like a plant something in one environment, and they get switched to another environment, and it asks you like how long does it take to heat up or something like that. Another type of question which is related to this is often they have something which is like they have a glass of coffee or they have a glass of tea, and they have this glass of coffee and tea and it's too hot to drink, so they set it on a counter and leave it according to the ambient temperature to allow it to cool. So this is using essentially Newton's law of cooling, and it's just based on the fact that if you put something which is warmer in a cooler environment, that heat will be lost to the environment, and eventually that cup, the thing in the cup, will cool down as well. So once again we have this kind of basic equation which is negative T minus Ts, where Ts is going to be the ambient temperature, and then we can kind of get from there the equation of our whatever the thing is. So whatever teacup, whatever the thing is. Cool. So yeah, essentially it's just first principles. Unless you want to use first principles, you can do that, but otherwise you can just remember this formula and plug it all in. Just like for this one, we could have memorized the formula as well. Cool. Alright, so let's have a go at this one. So this is kind of the type of question you'll get. So it's normally a fluid of some sort. So Nick takes a bottle of milk from the refrigerator for baby Alex. To heat this bottle, Nick places it in a saucepan of continually boiling water. Let Y be the temperature of the milk at time t after B's bottle is placed in the boiling water. So a differential equation that models this increase in temperature of the milk while the bowl is still in the boiling water is dy over dt equals to a 100 minus y, where a is bigger than 0. So what is the milk temperature when the bottle is put into the boiling water? So when is the milk temperature? The milk temperature when the boiling water is put into the they're just stating the milk temperature which when put into the boiling water is going to be 5 degrees. Sure. So they want us to solve the differential equation that y equals to 95 degrees where t is the time. So they want you to show that it's equivalent to this. So rather than verify, they say show that. So you're going to start from scratch as much as possible. So when it's just put into the boiling water, it's going to be 5 degrees. So what that actually means to us is y0 is going to be 5. Okay. And we also know what dy dt is, which is a 100 minus y. So from that, we can get dt over dy is equal to 1 over a 100 minus y. So we're going to get 1 on t minus 0 will equal to 1 on a times your antiderivative of from what will it be, y to 5, because it's 5 degrees initially, and it's going to be 1 over 100 minus y dy. So we'll get that TA or AT will be equivalent to log e 100 minus y, y5. So AT will be equal to log E 100 minus Y minus log E 95, which if we kind of simplify that down, it will be E to the AT will equal to 100 minus Y over 95, because we know Y cannot be bigger than 100. So if we kind of put that all in all, we'll get that this is going to be Y is equivalent to 95. Let me just rewrite that first part. So it's just a bit of rearranging here. So it will be 100 minus 95 e to the AT as required. Cool. So you can kind of see how we introduced the variable, put them in, flipped it over until we got the variable that we wanted, and then from there we can kind of figure out how to rearrange it in terms of t, so it's y in terms of t. Alright, cool. So this is often the trickiest type of question. So it's about these concentration of mixing problems. So it's often this type of question where you have a mixture being poured in and that mixture is flowing out as well. So what happens is you need to figure out the inflow and the outflow amount. So they're mostly given in grams per minute, and the main thing is to consider the inflow and outflow as separate things. So you have your inflow part, which is the amount they tell you in terms of the concentration, and this is going to be your flow rate, right? And that's going to essentially give you your amount per grams per minute times your flow in. And then your outflow is going to essentially be however much salt was in the tank over the volume plus whatever the change in volume is times your flow as well out. And so what that overall is going to give you is you can just multiply that to get that flow amount. So it's really important to remember that you will normally get what this value is. So the main thing is actually in figuring out the concentration is figuring out how much volume is actually occurring at each time, rather than actually focusing on this component, because this component will be really hard to isolate by itself. Cool. So if they do give you initial conditions, they don't count for this. You have to use later for the plus C. So you'll have to kind of put this in first and then use the plus C. Cool. So the main things is that there's two different types of situations. So the inflow can equal to the outflow, or the inflow is not going to equal to the outflow. And the main thing that it's going to change here is this one, right? Because the inflow here won't be affected regardless of if, the inflow is 3 liters above the outflow or 5 liters above the outflow. All in all, if it was 3 liters or 5 liters to begin with, that's however much the outflow rate is going to be, or the outflow kind of concentration gradient is going to be. But in terms of the outflow, so in terms of the inflow it won't matter, but in terms of the outflow, the main thing that's going to change is down here. So even though the amount of salt isn't going to change, the amount of volume is going to change, which means, so as the volume dilutes, it's going to dilute whatever the solid was in there before. So that means that the actual concentration will fall, which is going to affect the outflow rate. So the main two situations here, like we talked about, is when they're equal and when they're not equal. So if they're not equal, the easiest thing to do is essentially go V in minus V out, and that's what I like to do. So essentially I go that this is my V initial plus my V in minus our V out. So that way if they both cancel out, peachy days. If they don't cancel out, you still don't forget about the effect of volume on your concentration. Okay, in terms of the steps, you want to draw the situation. You want to put an inflow, outflow track, and also the capacity of the tank. So something like that. And then you want to define your inflow and outflow formulas. And that just includes writing out how fast it's going in and also what's the concentration going in. Same thing here. How fast is it coming out and what's the concentration of the thing that's coming out. And then what you want to find is this amount is going in and this amount is coming out. So the main thing you want to find here is what is the difference in those two amounts. So how much salt is going in and how much salt is going out. And then what you want to do is you just want to solve for that equation and find whatever the Q value is in terms of T. Alright, so if we look at this one, cordial has 3 grams of sugar. Before selling it, it needs to be diluted to a solution of cordial that flows into a tank initially filled with 100 of liters of water, which contains 20 grams of sugar. It enters the tank at 5 liters per unit, and a uniform mix flows out at the same rate. Solve the differential equation for the amount of sugar in the mix. So we draw out our tank, we have something coming out of our tank, and we can have stuff going into our tank as well. So there's 100 liters initially, and there's 20 grams initially in the tank. So i.e., let's say sugar, so sugar 0 is going to equal to 20, right? Or 20 grams. Okay, so then we go in and then come out. So in terms of in, it's going at 5 liters per minute, and out is going 5 liters per minute. In terms of the concentration going in, we said that's going to be, so concentration is going to equal to 3 grams per liter. And in terms of what's coming out, if we name that S, so that was going to be, the concentration coming out would have just been S over your 100 liters plus your 5 minus your 5. So all in all, it's just going to be S over 500. So what we're going to get here is now we can combine them. So therefore ds dt is going to be equivalent to ds dt in minus ds dt out. So what you're going to get here is, in terms of your ds dt in, you're going to get that it's going to be 3 grams, right, times your 5 liters. So it's going to be 15 of these grams that go in per minute, right? So you have you have the 3 liters per gram, 3 grams per liter, you have your 3 grams per liter, and you have your rate of 5, so you have 15 kind of grams going in at one time. In terms of coming out, you're going to have your 5 times your S over 100, which is essentially going to just be C over 20 in terms of your amount that you're going to get in. So you're going to get ds dt is going to be equivalent to this. And they wanted us to solve it here, so that means that we need to do a bit more magic to allow this to work. So we got that this is going to be S over 20, and whereas this is just 15, right? So therefore we can say ds dt is going to be equal to 300 minus S over 20. So what we can say here is dt ds is going to be equivalent to 20 over 300 minus x ds. dt, sorry, not ds. Yes, ds, not d. So it's going to be equivalent to that, and then if you wanted to find t is just going to be equivalent to this ds. Cool. So then what we're going to get here is that we're going to get that this part at the bottom is going to chuck a negative out front, and we're going to have log n of our 300, so log negative 20 log n of our 300 minus our s. And that's going to be equal to our s value, right? Or it's going to be equivalent to our t value. So therefore what you're going to get here is that e to the power of negative 20 t is going to equal to 300 minus s. So you'll get that your s is going to be equivalent to 300 minus e to the negative 20t in terms of your amount of fluid and how much salt you have in the mixture. Cool. Alright. Let me know if there's any questions. So a visual representation of these is essentially called a slope field. So a slope field, like the name suggests, shows the slope of graphs. So it literally just dots out what the shape of the graph will be, and it helps you visually represent what a family of curves actually looks like. So you can kind of see how they just all shifted up or down based on which one that you're looking at. And kind of note with these slope fields, it doesn't necessarily have to pass perfectly through each slope line. The main thing is that you need to make sure that you've matched your initial value well. So just make sure you're comfortable with at least doing a couple of these and see how you go with tracing them, because sometimes the tracing them can go a bit wonky because you follow a different path compared to what they've followed, and then you can kind of get a vastly different graph from there. Because if you might follow this one, you might see that it's a bit more curved, or if you look at this one, if you use like this here, right, so if you use like this point here, you can kind of see how that one passes through that point, but it might not pass through, let's say, like, we might go through that line instead, and then instead go more vertically. So there is a bit of leeway, but just make sure you get the point that they tell you exactly on the dot, and just try and trace as carefully as possible in terms of where it's going to be moving after that. And they will have a general shape in which you can follow, so just try and follow that shape. Alright, so this is calculator work, how it works in the calculator. So essentially what you do is you just like open your menu, and then there's a section where you can actually put in your differential equations directly in. The most important thing with this is that if you have your y being y1, it's important for you to type y1 in replacing your y component in your calculator. And similarly, if you're dealing with y2 or y3 or anything like that, just make sure to replace the letter that you've put in to make it clear to your calculator what you're actually talking about, because otherwise your calculator will refuse to do it. Cool. Alright, so in terms of slope fields, how we kind of identify them, so quick things to identify. So there's kind of a couple things that I think of in slope fields. So I first say, do I actually recognize the graph? Do I know what the graph is actually going to be? And is it like a polynomial, or is it a circular function? So do I already have a shape that I've already identified that I know? So that's one thing, right? That's kind of the key thing. The second thing is now I'm going to start looking like along the axes. So I'm going to try and find when x equals to 0, so along here or along here. So if x equals to 0 here, I'm going to check whether that makes the graph undefined or makes the graph, completely flat along there. So that will indicate to me that x is either a factor or x is going to be underneath the graph, depending on whether it becomes undefined or if it becomes, just horizontal. Then what I'm also going to do is when I anchor it at a certain x point, I'm just going to look down the values like this. So I'm going to check at x equals to 1, for example, and I'm going to browse down the slope lines. And I'm going to check that all the slope lines are the same, right? So if I check that, if all the slope lines are the same, that means that the graph is solely going to depend on x, because if x is not changing, the slope is not changing. And I can do something similar for the y values as well. So if I move horizontally like this and the gradient doesn't change, that means that the dy dx would have solely depended on the y values, because the slopes aren't changing when we move horizontally. So that's a good way to check it. Another thing I've kind of already mentioned, but looking for asymptotes where they're undefined is really important. And then also you can kind of look diagonally. So you want to look for areas where your gradient is positive, gradient negative, and what happens in terms of the transition. So those are a couple of things that you can look for. And you can also look for like vertical lines, which indicate asymptotes, and horizontal lines, which might indicate stationary points. And you can also look for, if you know that it looks like a circle, you can also look for the center as well to give you a bit more information. Cool. So we want to look at the y-axis, x-axis for patterns. So like we talked about, zero gradients, undefined, positive or negative. And then you want to look at the question. So we want to see if there's like vertical lines. So we want to look at the dy, dx's in terms of the options they give us. Because most of the time these questions are going to be multiple choice questions. I've seen like one or two off where they give you a slope field or they ask you to draw a slope field and then they might ask you to trace something. It's kind of a bit more rare compared to questions because it's a really easy VCA question. All they have to do is like generate a slope field on their calculators and then put it onto the exam and ask you what slope field it is. So it's a really good, easy question for them to ask, and they often like doing it. So being comfortable with kind of ruling out different derivatives or differential equations is really important. So look in the differential equation for any undefined lines, any zero gradients, where it's positive or negative. And you can also draw the graph on the slope field. So remember, if you get stuck, you're in exam 2, you can always use your calculator as well. So you can graph out each of the different slopes. And my main tip for that is to make sure that the axis you set is the same as the axis that you see on the page, because that will make it a lot easier for you to compare between the two. And you can also set different amounts of like dashes in your graph as well, because that way you can also change how many dashes and the general trend of the graph you're going to see. Cool. So for a question like this, so the differential equation is best represented, the differential equation that best represents the above derivative field. So you'll note that you can kind of see this like X type pattern. So I actually think this is going to be like a north-south hyperbola type situation. So something like this in terms of the actual graph itself, right? You can kind of see how it vaguely has that type of shape. So that means that it's going to involve both the X and Y. So we can do our tests, right? So if we move along this axis right here, so if we kind of move along the, it's a bit hard to see, but if you kind of move along the vertical axis here, I can see that the lines are kind of going straight down like that. So they're going straight down. You can kind of see how lines are going straight down. So what you can imagine here is that there is going to be some sort of asymptote when y equals to 0, right? So you know that you can see that there is some type of asymptote when y will equal to 0. So you know that you're ruling out essentially that you have a y at the bottom of your equation. You don't know what else you have at the bottom of the equation, but you know you have a y at the bottom of your equation. So that automatically rules out option A and option B. So then what you're going to do here is look for do the same thing except with the x coordinates. So you're going to look down the x, and you can kind of see that when x equals to 0, your gradient is going to equal to 0. So you know you have an x at the top at least. So you know that this so far is approximately what it looks like, right? So you know that there's an x and a y. So you can kind of rule out that option as well. So now we're just left with negative x over y and x over y. So those are our two options which are still available. The only difference between these two is that this is negative and this is positive. So what we want to look for here is we want to look for when x and y are both positive. So this is going to be in this quadrant right here, right? And we want to make sure that all of the gradients here within this quadrant are positive. And we can kind of see that is because they're all facing this way. And then we can do that double check, and we can check here as well. All the gradients here are positive as well. So if x is negative, y is negative, all the gradients are positive. And then we can check across here. So these are all negative, these are both positive, and that works out to be that it's just x over y. If it was this one instead, the orders would be reversed. So we would have positive in these two quadrants, because essentially you would have one being positive, one being negative, and then the extra negative would have made the gradients positive, and you would have negative in those quadrants. So we end up with option E here. And you can kind of see how these types of equations are just essentially ruling out ruling out the options you have until you can find what's going on. And that's why they do lots of multiple choice options with these, because these questions are actually quite hard to do unless you have a calculator, and unless you have a calculator, or unless it's a really simple differential equation to work with. Cool. All right. So let's talk a little bit about Euler's method, or Euler's method. So it's the same Euler who made Euler's number, and essentially this is the Euler's method, right? So this is kind of similar to talking about when you're talking about the whole idea of getting this one, which was using the fundamental theorem, using the fundamental theory of calculus. So it was under that idea that essentially if you want what FB is, you can find what FB is, or just FB essentially. FB is by just going from B to A of f dash of x dx plus f of A. So it comes from that idea, because you can kind of see parallels, right? So if you want the next value along your line, I'll just clear this. So if you want your next value along your line, along this thing here, what the most important thing to do is, if you want that next value along the line, you want to know where you're coming from, what is the slope of the change, what is the length of the change, and that will give you the height of the change, right? So essentially this is like rise over run, right? And then you're timesing it by its run, so you'll get the rise. So therefore you add the rise to the previous y value to get the overall y value. So the whole thing is that you use this y value as your anchor point, and you're using this one as like the change in y. So this whole thing represents the change in y. So the easiest thing to do with this is, honestly, it's often not that common to come up as it's not an uncommon question, but it's not a very common question. So you can make you can code your calculator to do this for you if you can make up an algorithm for it. I would say if you have the time, sure, do it. This might be something worthwhile, and it might help you get it into your brain as well. But I would say if you are a bit short on time, or if you have a lot of other stacks to revise for, it's probably not something I would bother with too much, because as long as you understand the method and what you're inputting, it often works out quite smoothly, and your calculator does most of the calculations for you anyway. Cool. So essentially the steps here is you write your y1 plus your yn, and then you put, so that's your the formula itself, and you want to count how many steps you want to do. So they might say something like you want to get from 1 to 2, and your step size is going to be 0.5. So you're going to go 1.5 and then 2. That's 2 steps, right? So you need to count how many steps you need first. And another thing is that can be really easy to mess up is this one is going to be the previous y and x values rather than the y and x values of the current thing, so of the current one. And the reasoning behind that is, if you think of the whole idea of it, essentially if you know this value and you want this value, you want to draw a line from this value to kind of project where that value might be. And obviously it's going to be off because this is an estimation method, but the whole idea is you kind of draw a line to estimate where that line is going, and then you essentially times it by the run to get the rise out of it. So then what you can do is you can just do step by step. So often, at most, they normally do about 3 steps for actual, not calculus, but actual exam questions. They normally do about 3 or 4 steps, maybe 3. I would say mostly 3. For textbooks, they might get you to do infinity and beyond, honestly, but it's just for practice and just so you can get comfortable with it. So in terms of something that you can code in, you can code in that as well. So you can write dy dx, all of this put in, and you can write the Euler's thing. So you can kind of see how this works here, because the gradient is rise over run, right? So if we wanted the gradient for this one, it would have been yn plus 1 minus yn over x plus 1 over xn, and this one is our run, which we've named our h value. So if you multiply out by that, you'll just get yn plus 1 minus yn. So that will give you, so if you kind of multiply it by that, you'll get yn plus 1 minus yn, so the yns will cancel out and you'll end up with yn plus 1. Same thing as, like I said before, with that whole concept of like the fb equals to b to a, b to a f of x dx plus f of a, because if you imagine what's going on with this one, essentially you're saying that fb will equal to, sorry, this should be f dash, so it's the gradient that you're looking at. So if you antiderive that, that should just be the normal graph, right? So just be fx, ba plus fa. So what you're going to get here is that it's going to be fb minus fa plus fa. So you can kind of see how those two cancel out like that. And it will leave you with fb. Cool. So let's have a try of this now. So use the Euler's method to find an approximation to the solution dy dx equals to 2x for the interval 0 to 3, given that y0 equals to 0 and x0 equals to 0 using a step size of 1. So first we need to identify how many things we need to do. So we need to go from 0 to 1, 1 to 2, and then 2 to 3. So we can calculate 1, 2, 3 steps. We need to go 3 steps in total. Okay, so our equation is y, I'd like to name it y1 if I want to move on. So y1 equals to y0 plus h f x0, and you can, so the reason why they include here yn and xn is sometimes because, like we've seen with our differential equations, the derivatives don't just include x, they include y as well, so that's why they include both when they're talking about this. Most of the cases it actually will just be x by itself. Sometimes you'll have the y, but that just means that you need both values to be subbed in, which is fine, you know. It doesn't actually make that much difference to what you're going to do. It just means that you have to sub in extra value. Cool. So what we can get here is essentially we'll get that this is going to be y1 equal to y0, which is 0, plus h, which is 1, times f of 0. So f 2x, which is just going to be 0, right? So we'll get that y1 will just equal to 0 as well. So y0 equals to 0, and y1 for us also equals to 0. Okay, cool. So we'll move on to y2 now. So y2 for us is going to be y1 plus h fx1. So our fx1 is our y1 is going to be 0 from our previous question, and our h is going to be 1, and our fx1 is now going to be essentially this value plus 1, right? Because we just worked out that that's the next value along. So again, it's going to be this one. So this is y0, y1, y2, y3. So y1, which is going to just be 1, so 2 times 1. So we're going to work that out to just be 2. Alright, so then we want to move on to our y. So our y2 is 2. So essentially that's what we're going to get here in terms of our value. So we move from y0, so this should be this is y1. So essentially when x equals to 1, you have y equaling to, so when x equals to 1, y equals to 0. When x equals to 2, y equals to 2. So therefore we'll move on to y3 now. So when y equals to 3, when x equals to 3, you're essentially going to get that this is going to be y2 plus h f x2. So that's going to be 2 plus 1 times x2, which is going to be 2 times 2 in terms of our value. So we're going to get this is 2 plus 4, which is going to equal to 6. So therefore you'll get that the approximation to the solution for the interval of this to this is that you'll get that at x equals to 3, y will equal to 6, approximately. You can do a bit of an approximate. And really important here, don't skip steps because it can get really easy to mess up. So because it's an approximation value, they'll ask you whether it's over an estimation or underestimation. So what you want to do is essentially just differentiate it and then just compare it. So like for this previous one here, right? So if we anti-differentiated this one here, so if we anti-differentiated this one here and to kind of find the value that we wanted, we would get that this is going to just be x squared, right? X squared and then essentially plus 0 overall, right? And then if we wanted to kind of find out what the actual value was, we would get that y equals x squared plus 0. So therefore, if we substitute that in, we'll get that y actually equals to 9 in reality. So we can see that that is an underestimation of the value of what y would be. Coolios. Alright. So let's move on to an example of doing that. So bacteria are spreading all over the petri dish modeled by this rate, where P is the proportion of the dish covered after T hours. Express 2 over P1 minus P in partial fraction form. So partial fractions to us, very helpful, great things for basically anything. So it's good to have all those partial fraction equations in your thing. So remember, if you have a linear factor, so just x minus a by itself, it just turns into a over x minus a. If you have a repeated factor, so x minus a squared, or let's say to the power of n, you're going to have a to the power of x minus a plus b to the power of x minus a squared until you have plus z over x minus a to the power of n. So you're going to do it that. And then the last one is going to be if you have ax squared plus bx plus c, where you have b squared minus 4ac is smaller than 0, so the discriminant is smaller than 0. And in that case, you're going to have bx plus c over ax squared plus bx plus c. So those are the kind of components, and you do a bit of a jigsaw thing. So for this, we just have two linear things, so we're going to express this as a over p plus b over 1 minus p. So what we can do here is essentially have a look at this, and we're going to say this is 2 over p 1 minus p. So if we times everything by p1 minus p, we're going to just get that this is 2a1 minus p plus b p. And we can just do a bit of collecting like terms here. So we're going to get that 0 is going to essentially just equal to b minus a, and you'll get that a is going to just be equivalent to 2. So what you're going to get here is that if a is equivalent to 2, p is also just going to be equivalent to 2. So if we want to express this in partial fraction form, what we're going to get is that it's going to be 2 over p plus 2 over 1 minus p. And we can do a quick test, so we'll have 2 minus 2p and then plus 2p, and that is equivalent. So the 2p's cancel out, so that's equivalent. Cool. Alright, so hence show by integration that t minus c over 2 log e p minus p, where c is a constant of integration. Show that t minus c equals, yeah, cool. Alright, so we remember this is our equation that they wanted us to do. So our dp over our dt was equivalent to p over 2 1 minus p. So if we kind of undo this, we'll say that dt over dp is equivalent to 2 over p 1 minus p, which coincidentally is our p over 2 plus 2 over 1 minus p from before. So therefore, if we kind of do it from here to here, we can say from t to, they just did the constant of integration, so we can use that form that they wanted us in rather than doing the terminal one. So what we can do here is we can just say t is going to be equivalent to antiderivative of 2 over p plus 2 over 1 minus p dp, which is going to be equivalent just to 2 log e p minus 2 log e 1 minus p, because of the p being negative here, and then plus c at the end. So that's equivalent to t, and then we want to kind of make sure it's in that form that they wanted it in. So we can go t minus c over 2 to divide that out is going to be equal to log e p minus log e 1 minus p, which means that t minus c over 2 is going to be equivalent to log e p over 1 minus p. And then as p, and they've told us that p is equivalent to something, so as p is bigger than 0, smaller than 1, therefore you'll get that p is going to be bigger than 0, and 1 minus p is also going to be bigger than 0. So therefore you'll get that this is going to be t minus c over 2 will equal to log e p over 1 minus p, as they require. Cool. Alright, so if half of this petri dish is covered by bacteria at t equals to 0, express p in terms of t. So essentially what they want here is they want us to say that in terms of this equation, half of the petri dish was actually going to be covered by that point. And remember, our p-value is going to just be essentially telling us that the proportion of the dish that was covered after t hours. So essentially what they're saying is that p equals to a half at t equals to 0. So if we write that out in terms of our equation, which was t minus c over 2 equals to log e p over 1 minus p, I think. Yep. So then we can substitute that in. So we'll have that 0 minus 2 over c will equal to log e a half over a half, right? Because a half and then 1 minus a half is a half anyway. So we'll just get that negative c over 2 will equal to log e1. And log e1, remember, that's just equivalent to 0 because essentially e to the power of 0 equals to 1. So we'll get that c will equal to 0. So therefore all you're going to get here is t over 2 will equal to log e p over 1 minus p. So you'll get that e to the power of t over 2 will equal to p over 1 minus p. So you'll get that e to the power of t over 2 minus your e to the power of t over 2 times by your p is going to be equivalent to p. And then we can take all the p's to one side. So we'll have that p and put that onto the other side. So we'll have 1 plus e to the power of t over 2 will equal to e to the power of t over 2. So we'll get that p will just be equal to e to the power of t over 2 over 1 plus e to the power of t over 2 as our equation. Alright, so then after 1 hour, a toxin is added to the petri dish which harms the bacteria and reduces the rate of growth. So the differential equation that models the rate of growth is now going to be different, which is now going to be this instead. So they want us to find the limiting value of p, which is the maximum possible proportion of the petri dish that is covered by the bacteria, and give our answer to 3 decimal places. So in order for our max value covered by bacteria, essentially we need to solve for dp dt is equivalent to 0, right? Because this will show where our stationary points will occur. So what we're going to say is 0 is going to equal to p over 2, 1 minus p minus root p over 20. And what we can do once we do that is, because this is correct to 3 decimal places, they're probably suggesting for us to solve that onto our calculators. So that's exactly what we can do. Alternatively, another thing you could do here is you could move the root p over 20 onto the other side and do a bit of squaring, and by that you'll get like a polynomial which you can work out as well. But for our purposes, we can just do this instead. So we'll have p over 2, 1 minus p minus root p over root p over 20 is equivalent to 0 for p. So it gives us a couple of different values. So it tells us p could equal to 0, p could equal to 0.01, or p could equal to 0.89, right? And the key thing here is that we want to make sure that these are all possible. So you can kind of see how the maximum is already given by, you can like already look and see that that is the maximum that's going to be possible. But the main thing is that we want to make sure that this is going to be possible for our t value as well. So what you could do is evaluate this for our t value to make sure it was possible in the first place. So i.e. t is going to be bigger than your 0 or your 1. So what you can do here is essentially, if you go back to the previous equation here, you just want to substitute into this to make sure that it works out for that. So you can go e to the power of 1/2 over 1 plus the power of 1/2. So you can see that that's going to be 0.66 something, right? So you know that it's going to surpass that level in terms of when that's going to be. So therefore, the max coverage is going to be 0.894. And you can just say max proportion coverage, or however you want to say it. Yeah, and there's not really a unit for this one, I guess. So you can just leave it as is. Cool. Alright. So a little bit more to this question. So the total time t hours measured from time equals to 0 needed for the bacteria to cover 80% of the petri dish is given by this equation. So you can kind of see how that exactly is our fundamental kind of theorem of calculus type thing. So where Q, R, and S all belong to R. Find the values of Q, R, S, and giving the value of Q corrected 2 decimal places. Cool. So what we can see here is that it needs to cover 80% of the petri dish. So right away we need that P to equal to 0.8. We also want here that we want these two values to tell us when this is going to occur, right? So we want to know when exactly those two values are going to occur. And this thing is actually going to come from our own values of what's going to be going on. So this, in terms of like a time is going to require for this to happen, right? We want to know how much time it's going to be from t equals to 0. So what that means is that if we think of what's going on in terms of the timeline, in terms of how long it will actually take, right? It will take the time, so it will take the time of t, so however many seconds it is. So because this equation only works from t equals to 1, essentially what you need to do here is kind of measure it from t equals to 1. So what you're going to do is essentially you're going to say that this, if we were to set up this equation, it would essentially be that you have your, just rub that bit out actually. You have your dp dt from before. You have your dp dt from before, which was this one here, right? And you're going to say that's equivalent to your p over 2, 1 minus p, root p over 20, and that's how it's going to be converted into this one. So eventually you'll end up with t to 1, because you're essentially going to add that 1 second on at the end to find out when it's going to reach that point. T to 1 dt is going to be equivalent to saying that this is, so yeah, you flipped it over, so you flipped it over, and then it's going to be equivalent to saying that you want 80% to be covered, and you want to know how much is covered at t equals to 1, right? So essentially, t equals to 1, you want to know how much was covered at that point, which we coincidentally actually found for the previous one. And we know that's going to be 0.62245 ... So therefore this one here is going to be 0.26, so this is 0.8, 0.26, and this is 2 decimal places, so 0.62. and then we're going to have 1 over p over 2, 1 minus p minus root p over 20 dp, right? And then if we were to undo this one, and we can rub out that side so it's a bit cleaner, essentially it would just be t minus 1 in terms of the time, so t minus 1. And what we're going to get here is that, therefore we'll add the 1 to the other side, so we'll get that q, which is this one here, will be 0.62. Our r, which is up there, is going to be 0.8, and our s is just going to be 1. Cool. Alright, last part to this question. So given p equals to 0.75 when t equals to 3, use Euler's method with the step size of 0.5 to estimate the value of p when t equals to 3.5. So you can see that it goes from 3 to 3.5. So you can see that it's only going to be one step. Alright, and it's given 3 marks for that, which is quite kind, I guess. So P0 is going to equal to 0.75. I guess we can go with P3 actually instead to make it a bit easier to understand. So let's go with P3. So if we want P3.5, we're going to get, that's going to be P3 plus H, which is going to be our 0.5 here, times our, what was that function? So our dp dt at t equals to 3 and p3 equals to 0.75. So if we look at the equation we're going to use this one because t is bigger than 1 here. So that's the equation we're going to use. So if we put that in to our equation here, so p3 is 0.75 plus 0.5 of our equation dp dt was something like p over 2, 1 minus p minus root p over 20, I think. Let's just do a quick check. Yep, looks good. So therefore what we can do here is we can substitute that in, and so the t doesn't actually matter in here, so we can just leave that. So we'll have 0.75 over 2, 1 minus 0.75 minus 0.75 rooted over 20. And then we can put that all into our calculator, or you can find it by hand, up to you. But we can put this into our calculator, so 0.75 over 2 times 1 minus 0.75 minus your 0.75 rooted over your 20, which is going to be 0.05 something, and then you can times that by 0.5 to get you 0.025, and then you can plus that onto your 0.75 value, which all in all is going to give you equal to 0.775 ... So therefore p at t equals to 3.5 is going to be equivalent to 0.775. And there's not really a unit once again. Cool. Alright, so kind of summarizing differential equations, essentially there's a couple of different things that you can know. So the fundamental theorem of calculus, we've practiced that quite a bit with kind of separating the values on both sides. The separation of values, so essentially that dodgy maths where you move one thing to one side and the other thing to the other side and kind of separate it out and do the anti-differentiation of both sides at once, and make sure to put the integrals in as soon as you do the separation. There's growth and decay, which works with the differential equation as well, and with cooling and with the growth or decay of bacteria. And we also talked about the different problems, so the cooling problem and then also the mixing problem, which is to do with the inflow-outflow type problems, and just make sure you know whether the volume is changing or it's staying constant. And the last couple bits was looking at slope fields, so make sure to look for patterns, make sure to look for when y equals 0, x equals 0, make sure to look when things are positive, things are negative. And then we also talked about Euler's method, which really is important to organize your working well in terms of what you're doing. Cool. Alright, so we'll move on to talking a little bit about kinematics now. So kinematics is not as big as a topic as it used to be. So in the old special study design, there was kinematics, dynamics, statics, like a whole lot of motion stuff, whole lot of force stuff. So that whole motion topic has been scrapped and replaced with logic and proof, essentially. So it's still something that you'll have to do because we still need to learn vector calculus, but fortunately we don't actually have to know all of it as in detail as we did before, but we just have to know the kinematic side rather than the force side. I've still included some slides on force just to give you some context because it might come up in SACs and they still might ask about it in examinations as well, but they will give you extra information to actually tell you what it is because it's no longer assumed knowledge. Okay, so different motion variables, and you will hear about this both in spec and in methods. So you can have vector quantities and scalar quantities. So vector quantities you'll all be really familiar with. Vectors are essentially things that have a magnitude and a direction. So stuff like displacement, velocity, acceleration, and then the scalar equivalents like distance, speed, and acceleration. So acceleration can be both. So one thing that they like to do is like a velocity time graph. And why they like to do a velocity time graph is because everything on a velocity time graph indicates something. So the gradient will indicate acceleration, the coordinate where it sits will evidently indicate velocity, and the area under the graph will indicate the displacement or distance, depending on how you calculate the area. So in terms of going from position to velocity to acceleration, you are going to differentiate, and then if you're going the other way around, you're essentially just going to anti-differentiate. So that's a relationship between the two. So it's really important that you know the difference between displacement and distance. So displacement is the change in position from the original. So if I come here and then I go whoop, 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 and I end up here, right? My displacement is going to be 2 units from here. However, the distance I moved is this whole line over there, right? So it's going to be up to 3, then backwards to 2.5, negative 2.5, and then I'm going to go up to 3 again, then I'm going to go back to 2. So if I was counting the number of units, it would be 3 plus 5.5, so 8.5, and then I go back to 3, so plus another 5.5, so 14. Is that right? So 3.5, 8.5. Yeah, 14. Oh, no. Yeah, 14. So you go 14. So essentially you go 3 up and then 11 back and forth. So 14, and then we go back 1 unit. So essentially it would be 15 units in total in terms of the movement, right? But actually displacement, because it's a vector thing, we'll say that it's 2 units positive, right? So it's very different, and you look at different things on your area graphs as well in terms of looking at your velocity time graphs. So in terms of our velocity and speed, there's a couple different ways to measure it and a couple different ways to talk about it as well. So you have your average rates of change, so y1 over y2 over time essentially. So instead of your y1, y2 over y1, you're going to have your x2 over x1 because your x generally shows your displacement. So now it's your dependent type thing that you're going to be working with. And so now over time, right? So essentially it's just like distance or displacement over time, and that's your average velocity. Your distance over time is going to be your average speed, so it's important that you find the total distance and then divide by the total thing. So your average velocity is not same thing as your average speed, because your average velocity will show like for that previous one, if we were talking about the average velocity between here and here, it would be 2 minus 0 over, let's say, 3 seconds, whereas the other one would be 15 over 3 seconds. So very, very different. And the instantaneous velocity is just going to be your derivative, so your dx over dt in terms of your differentiation. And it's always specified in meters per second, because it's just the easiest, honestly. And it's the one that's, it's like things with most things in mathematics, it's just convention. They chose one thing and then they just kind of moved with it. So always just using meters per second as your conventional unit. Unless they tell you, you can always check with the question. In terms of acceleration, so our average acceleration is going to be essentially just v2 minus v1 over time. So I change in velocity over time, and our instantaneous is going to be the derivative of velocity. So make sure that you want to know that this idea of direction of travel is really important. So your direction of travel is going to be given by your velocity, not your acceleration, because your acceleration might be acting in the opposite direction to your velocity because you're slowing down. So just keep that in mind. Cool. So there is a couple of different things that you want to kind of think about, and because they will tell you these things in like a whole blurb of information, and you want to be able to extract the little pieces of information which are most important to the topic that you're doing and most important to what you're talking about, right? So initially it's going to be t equals to 0, at rest v equals to 0, uniform or constant acceleration a equals to constant, where, i.e. what's x, when t equals to something, eventually long term, so terminal velocity is a equals to 0 t when t goes to infinity, and acceleration due to gravity is negative 9.8, or it's 10 depending on what the question tells you. So just in terms of acceleration, because it is by nature a vector quantity, you kind of do have to specify which direction you're talking about. And even when you see this in methods as well, technically you're still dealing with a bit of vector stuff, because you don't make it obvious you're dealing with vectors, but you still say stuff like, oh, going up, going down, right? And that evidently is talking about direction. So making sure in these types of questions to specify exactly which direction is positive, which direction is negative, somewhere like clearly actually write it down, makes it easier for you to cognitively actually refer to that, so that you don't get confused which one is up and down, and you don't get confused about which ones you have to make positive and which ones you have to make negative. Cool. Alright, SUVAT rules. These are super duper helpful. Learn them, love them, be them, because essentially your alternative is that you have to do differentiation or anti-differentiation to find all of these things. So what I recommend, have these in your bound notes, but get comfortable with using them because they're not on your formula sheet. So get comfortable with using them. They're called the SUVAT formulas because that stands for each of the acronyms. So S for displacement, U for initial velocity, V for final velocity, A for acceleration, and T for time. And you have all of these equations here. And most of them actually make quite a lot of sense because, what you're actually going to say is that, okay, so what's my final velocity? My final velocity is going to be my initial velocity plus my acceleration times my time, because that's going to give my velocity change, right? So most of these formulas can make quite a bit of sense. The most important thing is that you must have a constant acceleration to use this. So if your acceleration is affected by anything which has an equation in it, you will no longer be able to use these because your acceleration is no longer going to be by definition constant anymore. So these are constant acceleration formulas. So just keep that in mind. Cool. Alright. So you want to say, is your acceleration uniform? If it's uniform or not, you want to be able to say, okay, then I can use my SUVAT formulas. Define your positive direction of motion and literally write it on the page because it will make your life easier so that you don't get confused when you're referring back or checking over your answers. Define the given info. So literally just write V equals this, U equals this. And what I recommend is just like as you read the information, just write out whatever it is. So S equals to this, T equals to this, whatever you want. And then what you want to do is you want to write V equals to this, U equals to this, S equals to this, A equals to this, T equals to this. And you'll find with each of these SUVAT equations that you have 3 variables generally. So 1, 2, 3, right? And 1, 2, 3, 4. So there's 4 variables, or So 1, 2, 3, 4, sorry. You generally have 4 variables. So you have 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4. So you can see how there's 4 variables involved in each of these. So you'll have one variable which is not involved in the equation or not mentioned. So you don't need to care about that. But you'll know 3 other ones, and your last one will be the question mark. So you essentially want to just find the equation which has all 4 of those variables in it. And that will allow you to find what you need to find. And you apply the equation and do whatever you need to do. And you can draw things out as well if that's helpful. Alright, so a special case of this is projectile motion, and it's mostly SAVAT related. So sometimes they start off with something which is constant acceleration related, and then they kind of like merge into something which is less constant acceleration-y. So they start with something which is talking about, this person throws a ball according to gravity, bloody yada yada, and then suddenly they have a gust of wind which goes at a velocity of bloody bloody, and suddenly now you don't have a constant acceleration anymore. So just be a little bit aware of that, because that can be a little bit dangerous in terms of doing the question, because you assume constant acceleration and then you get to a certain point and you're like, oh, it's not constant acceleration anymore. So it's often when you drop or shoot something in the air, or if it's like bounced off a cliff as well sometimes. So normally there is no horizontal translation unless stated. So unless there is something which is an engine propelling forward, you don't really have a horizontal translation. You just have the initial horizontal velocity, which is going that way. And because of there's no acceleration, normally also there's nothing stopping the ball from going that way. So stopping the ball from going horizontally, unless it kind of falls into the ground, right? Because then it wouldn't. You would think about it, and you're like, oh, technically there's still not really a force acting on it. But if you think about it in practical means, it's probably just like the ground and the friction of the ground which is stopping it rolling. So if you think of a ball being thrown, right? Normally the ball goes woo, and it hits the ground, and it does a bit of a roll forward as well, because it's still moving horizontally, but it's not moving vertically anymore. So the most important thing is just to kind of recognize that. So the speed is always constant unless there's air resistance, so there's no other forces acting on it. Vertically, the direction is really important, so just make one direction positive, one direction negative in terms of up and down, and that way you can decide whether acceleration is positive or negative. And you can just use your SAVAT equations for finding all of this type of stuff. So just think about what's happening. So at the top of the motion, that's when velocity is going to equal to 0 up here. And then, here you have your initial velocity, whatever that is. And down here as well, you're going to think that. So, and the funny thing with these projectile motion questions is that if you go up like this, right, the amount of speed going up here and the amount of speed going down here is often going to be equivalent, because essentially it gains speed, and then loses the speed in the same amount, as long as there's no other forces except gravity acting on it. So that's also something that can commonly occur. Okay, so let's have a go at this type of question. So a rocket ascends with a uniform velocity of 15 meters per second. When the rocket ascends like this. That's a horrible rocket, sorry. So it goes up 15 meters per second, and then when it's 80 meters above the ground, the screw drops out of the rocket. Ignore air resistance. How long will it take for the screw to reach the ground? So this screw is reaching the ground, essentially. So this screw is initially going up at a thing of 15 meters per second, and I'm going to let up be positive. So what that means for us is it tells us no other things are acting on it, so we're quite comfortable that it's constant acceleration. So my initial velocity is going to be 15, right? My final velocity is going to be 0, because that's when I want it to hit. Actually, rather than my final velocity being 0, because it might be hitting the ground quite quickly, and that's also something else that we want to find, so I'll just rub that out. Because the final velocity would find the top bit rather than the bottom bit. So I want my u to equal to 15. I want my s to equal to negative 80. And I want my acceleration to equal to negative 9.8 or negative 10, depending on what they tell us. And the things I'm trying to find here is t and v. So we can go with maybe t first. So the equation for t is SUT plus a half AT squared. So we'll say that negative AT will equal to 15 times t plus a half negative 9.8 t squared. And you can probably solve this just by hand, but we can just pop it into our calculators just for, efficiency's sake. So you can solve it by hand using Pythag or however you like to solve it, but essentially you plug the values in and you should be able to get something quite nice quite easily. And often they'll use 10 in an actual exam 1 question just to make your life a little bit easier so you don't have to think as much about what's going on. So the values you're going to get here is t equals to negative 2.7 something, and t will equal to 5 point something, 5.8 something. Evidently t has to be greater than 0, so therefore you're going to go with your t equals to 5.8. Well, let's go with 5.9 if we round it up. So 5.9 seconds. And then we also want our v. So our v in terms of our equation is we can do this one. So we can say S equals to U plus V. Oh, let me think of which equation would be the best one to use for this one, so we don't have to involve our t value as well. So we want to find the one which just has UAS, so this one here. So we can say that v squared equals u squared plus 2as. So we want v squared to equal to 15 squared plus 2, negative 9.8, negative 80. So we can put that into our equation. So we want 15 squared plus 2 times negative 9.8 times negative 80. And that's going to be that. So we can root that now. So it's going to be going at a velocity of 42.334, and it's going to be going downwards, evidently, into the ground. Cool, amazing. All right. So these are the other acceleration formulas that you'll get, and these are particularly popular in MCQ questions. They're really popular for those. So it's really important that you know the different ones that you can represent acceleration by. This one, and this one are probably the most popular ones. So just make sure you know how to represent these. So if you have your acceleration in terms of t, evidently you can just use the dv dt formula for it. If it's in terms of v, right? So if the initial value has v and t in it, what you can do is essentially just flip it. So you say dt over dv equals 1 over fv. If you have fx or fv and you have v and x, that means that you need to do a bit of a switcheroo and use this formula instead. And you can ask me, why does this formula even work? And essentially it's because dv is essentially dx over dt, and if you times that by dv over dt, being dv over dx, the x's cancel out, so it gives you the same thing. And if it's just solely in terms of x and it has v and x, another formula you can use is this one. And this one essentially just comes from the idea that you can do this same thing, except you're just going to move it to the other side. So you're going to anti-diff the v part already on the other side. So you just essentially move the v over. So what you're going to do is you move the v over in the process itself, and then that kind of already gets rid of the v. So you're anti-diffing v dv essentially, which gives you a half v squared. Righty, vector calculus. So this is kind of like an extension of the kinematics and all the stuff we've learnt to the universe of vectors. So essentially what we think of as vector calculus, it's not much more complicated than vectors. Essentially the only thing we're adding onto the idea of vectors is that instead of having numbers for each of the positions of each of the planes, we just now have equations instead, which means that we can do a lot more with them. So we're talking about motion in this plane, and that plane. So there's a couple different things that they can ask us to do with this. Obviously, they can ask us to do all the kinematics, motion stuff. They can also ask us to do things about sketching pathways. So in order to convey a vector equation into a Cartesian equation, and this will normally be done if it only has I and J components, because we don't really work with 3D stuff very much. So all you have to do is essentially convert this, so you make this equivalent to x and this equivalent to y, and then you make them equal, and then there'll be a parameter. You work with the parametric equations, manipulate them so you're able to get y in terms of x, or at least like in a form which is a relation, a type of relation that you know. And then once you do that, essentially all you need to do after that is just tidy it up and make it nice so that you can look at that. And then there will be normally a domain and a range for the parameter involved in it. So normally t, they might say t is between 0 and 20 or something like that. And by doing that, you just have to sub it into the x and the y equations to figure out what the domain and range is. And then you can just draw whatever it is and make sure to state the direction of motion. And how you can test the direction of the motion is essentially just like if you just go sub in t equals to 0 and then t equals to 1 or t equals to 2, sub in easy values, and that will show you which direction it's kind of moving in. So the main things that they kind of assess you on is like the particle's motion, the shape, and then the starting direction and place. So, and then also the period as well, because often it's like pi or something in terms of, sometimes they're like circular functions, which means that period is important. And so yeah, you normally if they ask you to graph it, they'll say state the direction of motion and state the starting point, and you can just write that in. Cool. So for something like this, sketch the pathway defined by the following vector function, identify the starting position and direction of motion. So like I said, normally they'll ask for what they want. So we make this one equivalent to x and this one equivalent to y. So we'll have x will equal to 2 sine t and y will equal to 3 cos t. And why we make that first one equivalent to x and the second one equivalent to y is because I corresponds to the horizontal plane, and generally our x corresponds to our horizontal plane, and our j corresponds to the vertical plane, and generally our j, like our vertical plane, corresponds to our y. So that's why we have that. So this one you might be familiar with in terms of finding a parametric equation and converting this into a Cartesian equation. So all you need to do is utilize the sine squared plus cos squared equals to 1 here. So what we're going to say is sine theta is going to equal to x over 2, and cos theta is going to equal to y on 3. So what that means for us is we can just go x squared over 4 plus y squared over 9 is going to equal to 1. And that's going to be our equation. So what we know is it's going to look a bit like an oblong potato. So it's going to go from 2 to -2 and from 3 to -3. So you can watch me draw this oblong. Hopefully your oblong looks a bit better than mine. Sorry, it looks a bit potatoey, but it goes from 2 to -2 and -3 to 3. And then we want to also test the direction of motion. So we probably shouldn't have drawn it out yet. But we just want to test whether it's 0 to pi. So if we think of what 2 sine theta is going to look like in terms of our equation. So remember your sine theta graph, your theta graph goes like this, right? So it's kind of going to go like that, and it's going to come from 2 and -2. So up here is going to be pi on 2, so down here is going to be pi. So it's only actually going to be this half of the graph. So therefore we're going to actually say that it's going to be from 0 to 2. So I'm just going to rub out my oblong and redraw it because we need to fix up the domain and range. So we figure out that it's actually only between 0 and 2. So it's going to go up to here, which is 2. And then in terms of our cos graph, remember, it looks something like this. So it kind of hits the peak and then it goes to like this down here. So this is pi on 2, this is pi. So if we check what's going to be going on here, it's 0 to pi. So it's this section here. So we can check that's going to be from 3 to -3. So our y graph is going to still be from 3 to -3. So it's going to look like this, like a semi oblong or a semi ellipse. And then we can draw out our starting position now. So if we substitute 0 into there, sine 0 is going to equal to 0. So essentially it's going to end up that it's going to be here. So sine 0 is going to be along here. So the x coordinate is going to be 0. And then the y coordinate, if we sub 0 into there, so cos 0 is going to equal to 1. So this is going to be our starting point. So 0, 3, starting point. And we can kind of guess the direction of motion from here. It's not evidently not going to go that way, so it has to go this way, but we can do a quick check. So if we sub in pi on 2 into here, sine pi on 2 is going to equal to 1, so it's going to end up here. Means, sorry, 1 times 2, so it's going to end up here. And then cos pi on 2 is going to equal to 0, so that's 0, so we know that's going to end up here, so we can kind of draw that as the direction of motion. Amazing. Cool. Alright, so in terms of these are our kind of things that we look for. So just like we looked for displacement and distance in kinematics, we can do the same for vectors. So if we're looking for distance, we can kind of do this one, which essentially kind of looks like the length of curve graph, length of curve equation, and is essentially the length of curve equation if you have a bit of a squeeze at what's going on. So you're just looking at the arc length or the total area under that graph. So that's kind of what you can get there. If you're looking at the distance between 2 points, it's just r1 minus r2, and the direction of motion is going to be given. So here, when they ask you to label the direction of motion, it's like an arrow, but in terms of actually stating the direction of motion, it's going to be the velocity. So if they tell you to state what the direction of motion is, it's going to be like the actual velocity equation. So whatever it is. So state the direction of motion at t equals to 1. You're going to find the velocity and then substitute 1 into it. And this is really important in terms of crossing versus colliding. So crossing paths means that they can share the same x and y point, but not at the same time, whereas colliding is that they have the same x and y points at the exact same time. So i.e. x1 equals to x2 when y1 equals to y2. Whereas these ones, they might not be necessarily at that point. It's just that the actual equations cross. So an example of this is if we said, so here, right, we scheduled a time to start this lecture, and we said at this lecture on this website, right? So we collided because we were at the same place at the same time, right? And all of your peers who are listening to this as well, you're at the same place at the same time. Whereas, because this lecture is recorded, you might be listening to this a couple of days on, and you will be listening, and then you'll be listening then, but then somebody else will be listening a couple days ago. So you were at the same place, but you're not there at the same time. So you would not have collided. So when we talk about this, it's more in a physical sense. So I guess if you're talking about meeting up with a friend at school, you meet up, you tell them a place and a time, and you've collided because you're telling them the place and the time, so you're at the same place at the same time. Whereas if you're like, okay, we want to meet here, but nobody really specified what time you're going to meet, that means that you will have crossed paths probably, because you probably went past the same point, but it won't ever have been that you collided, because you will never be at the same point at the exact same time. Okay, another thing here also that they ask a lot is about the shortest distance. And to find the shortest distance, simply, we will just want to find the perpendicular to the curve and go straight there. So remember that with the dot products, that if you dot product two perpendicular vectors, it equals to 0. So essentially, if we want to find that, all we have to do is convert the point that we want to talk about into a vector. And then we want to subtract that from the curve vector, so subtract it from whatever this curve kind of is. And then what we want to do is multiply that against the curve vector. So we're saying essentially the distance vector here, and then we want to multiply it by that curve vector. And then what we want to do is solve that vector equals to 0, because we want that vector to be the minimum distance possible. So we want those two vectors to be perpendicular, right? So that's exactly what we're going to get. And essentially in terms of the actual distance formula, so once you find exactly what it is, then you can substitute it into this one to actually find what the actual distance per se is. Alright, so we'll move on to vector projectile motion now, and kind of talk a little bit about what happens there. So it's very similar to the kinetics motion that we just talked about before in terms of what's going on, and essentially it's the exact same thing, except the only kind of minute difference to it is that you now have vectors being involved. So it actually makes it easier because now you can resolve the vectors into two components rather than having to deal with both the vertical and the horizontal component as at once. And before, essentially what we did with kinematics is just like resolve it into two components, rather than we kind of talked about, this is the horizontal component, this is the vertical component. But now what we're going to do instead is just kind of change it. So instead it's going to be, we can kind of simultaneously talk about the two things because we're just separating it via the I and J type thing. So once we can do this, right, we will see that we'll be able to just essentially do the same thing. So we start with acceleration, and if we only have gravity here, and if we have extra things acting on it, we can do extra things. If not, you can still use the constant acceleration formulas, except the only difference here is that instead of just solely using the constant acceleration formulas, now you can kind of introduce the idea of vectors to that as well. Cool. So these are a couple laws that I just put in the slides for you to have a look at. Essentially, they're just the laws that you might come across in terms of your methods or your spec. And they're just things that can come up. They should explain it to you in questions because technically it's not formally part of the study design anymore. Okay. And these are the forces that also might come up. Alright, so last little bit is about talking about your language of proof. So these are just like a table summarizing all the different languages. I won't read them out to you because I'm sure you understand all the different types of languages, but essentially the different ideas is that you can negate things, and the idea is in order to prove something you need a premise and conclusion. So you need to assume something is true and then you're going to get something from that conclusion. There's a lot of different quantifiers, so there's the for all and there exists, which are our two main ones, and it kind of depends on which order it is in, whether it wants you to prove it as true or whether it wants you to prove it as not true. The idea of contrapositive is really important because we have a idea of proof by contrapositive, and we also have, so kind of like converse, contrapositive, and then you also have like a negation type thing. So each of those sound like the same thing, but essentially what it is they're both all quite different. The negation is the exact opposite of what's happening. The converse is just switching the order of the two statements, and the contrapositive is an equivalent statement. Cool. Alright, so let's do some all the different proofing techniques. So if you have n cubed, if n is even, essentially you don't need any fancy skills for this, but handy skills is to know what to represent as even, what to represent as odd. So if it's even, we can let n equal to 2k, where k belongs to z. And therefore what we can do here is we can say that n cubed will equal to 2k all cubed, right? And 2k all cubed is just going to be equivalent to 8k cubed. So n cubed equals to 8k cubed, right? So then we can make n cubed equivalent to 4k cubed. So therefore, n cubed is even if n is even. Cool. Alright, so proof by cases is the same thing, but you essentially just have it in little bits. So prove that if n squared is not divisible, so prove that n squared is not divisible by 3 if n is not divisible by 3. So we have a couple of cases for n not being divisible by 3. So n could equal to 2k plus 1, or n could equal to 2k plus 2. So in terms of this, n squared would equal to 4k squared plus 4k plus 1, right? So if we kind of tried to make that all equivalent to 3, or just try and get rid of that bit, we can kind of see that regardless of what we're working with, we'll see that, it's never going to be divisible by 3 because these 4k's, if we put in maybe, we could even like change this so it was instead kind of dealing with the 3's instead. So we can say, it's 3 then we can have k squared plus k, and then we'll have left over, you know, k squared plus k plus 1. And you can even actually group it like this as well. So if we get a bit of a rubber, so if we can also group it, so you can essentially say that if you put this into like kind of put it into the like make everything in terms of threes instead of like putting it like this, so you make all of this in terms of 3. You could even say that this is going to be equivalent to 3, you know, k plus, oh sorry, this should be 3k plus 1. Just realized that. 3k plus 1 and 3k plus 2. I was thinking of different things. 3k plus 1, 3k plus 2. So that means that you can do up here 9k squared plus 6k plus 1. So you can group the 3 on the outside, so you get 3k squared plus 2k plus 1, or n squared will equal to 9k squared plus 12k plus 4. So you can group the 3 once again. So you can have 3k squared plus, you can leave the 4 out to the back honestly, but also you can group it in. So 4k plus 1, so therefore not, if n is not divisible by 3, n squared is not divisible by 3. And I like to just restate the conclusion at the end because it just makes it really clear that we've proven it. Alright, so prove that root 2 is irrational. So this is a proof by contradiction. So what essentially the idea is you assume this is true and then you're going to get to a contradictory statement. So assume root 2 is rational. So what that means is root 2 will equal to p over q, where p and q belong to z. So therefore root 2q will equal to p, and therefore 2q will equal to p squared. So therefore p squared is even. And we can do the proof that if p squared is even, p squared is even, p is even. So that's essentially just taken from a proof by contrapositive, so we can do that. So a proof by contrapositive, the contrapositive statement is p is odd if p is odd, then p squared is odd. So we can say is p equals to 2k plus 1, so p squared would equal to 4k squared plus 4k plus 1. So we'll get that this is 2k squared plus 2k plus 1. So you can see that it would be odd as well. So we kind of proved that, so we can say p will let that equal to, say, 2l. So therefore we'll have 2q will equal to 4l squared, so q will equal to q squared will equal to 2l squared, so therefore q squared is even and q is even. But then you have a contradiction because now you're saying both is even. So therefore, root 2 must be irrational, as p and q cannot share factors. Cool. Alright, so proof by contrapositive, we just saw this exact statement. So essentially it's just switching the two statements and negating both, and that is equivalent to the original statement. Alright, last one down here is proof by mathematical induction. Fan favorite because it's very structured. So essentially you prove the base case and then you prove the general case is true, and then you do the induction step. So we can do these in this type of step. So we essentially let this Pn equal to this, and so P1 will be equivalent to, left hand side will be equivalent to 1, and right hand side will be equivalent to 1 over 2, 1 plus 1, which is equivalent to 1. So right hand side equals to left hand side. So P1 is true. Alright, so then assume PK is true. And that just essentially means that this whole statement, if k was there, would be true. So therefore we need to explore pk plus 1. So pk plus 1 would equal 1 plus 2 plus 3 ... until n minus 2 and plus, so n minus 1, n minus 2, I think that should be in the other way around, probably, n minus 2 and then n minus 1, n minus 1 and then plus n. So essentially we'll go with n minus 1 and then plus until it gets to n and then n plus 1, right? So our goal is to get this to k plus 1 plus 1. So what we can do here is we want this to be k, 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 and k. So all of this is going to condense just down to, using our pk type thing, it's going to condense to n over 2 n plus 1 plus n plus 1. So if we kind of just essentially group it, right, all we'll get here is that we'll get that this is going to be n plus 1, and then we'll be able to group this into the function so that we can kind of condense it a little bit. So what we'll get here is we'll be able to condense this to n plus 1, right, will be 1 plus n over 2, right? So we'll be able to get that this part is going to be, let's rub this out so we have a bit more space on our slide. So we know that P1, we already proved that P1 is true. And so this comes from our, we'll be very familiar because it just essentially comes from our sequence formula, which is essentially n over 2 is 2a plus n minus 1d. So if we kind of look at here, right, we'll sub in the 2, so we'll get 2 here, and then our d is essentially just 1. So if we put that into there, we'll just get that this is going to be 2 plus n minus 1, which is just going to be n plus 1. So if we kind of substitute into this formula, we'll get that pk plus 1 would have been equivalent to 1 plus 2 plus 3 ... until n plus 1, right? And we kind of just said how this thing from before was going to be equivalent to just our pk, so equivalent to our right hand side of our pk. So what we will get here is, like we said before, so pk will just equal to n over 2 n plus 1, and then we'll have plus n plus 1 at the end. And remember, our goal is to get to n plus 1 over 2, right, plus, or n plus 1 over 2 times our n plus 2 overall. So we can kind of expand this. So we can have n squared plus n over 2 plus n plus 1. And then we can kind of move this across. So we'll have that this is going to be n squared plus n plus 2n plus 2 over 2, right, all equal to our pk, which is going to condense to pk is equivalent to n squared plus 3n plus 2 over 2, which we can also rewrite as happiness n plus 1 over 2, n plus 2 as required. So therefore we can say that therefore pk plus 1 is true and p1 is true. So therefore your pn is true. Cool, amazing. So that's the last bit of information, and we went through kind of vector calculus and differential equations today, and then talked a bit about proofing. So just remember to work out this stuff regularly. All of the knowledge of this kind of just, you'll build up regularly and build up by applying to different questions. So thanks so much for listening. I will stick around to answer any questions, but otherwise thanks so much and good luck, and I'll see you around.